In this video, we will learn about the proof of a statement. For an integer x, the value of fx is a function, and the function is given x cubed plus x plus 1 is an odd integer. So in our exam, they will give us only these two lines that prove the following statement. For an integer, only these two lines that will be given. So how can we prove it? Because they have given x is an integer. This is the statement. You have to keep in mind that x is an integer. This is a hint for the solution, right? And then we have to prove that this fx is an odd integer. So how can we prove it? We will split this situation into two kinds, two types. One type is that we will suppose that because they have given that x is an integer, so integer may be positive or integer may be negative. So we have two conditions. When x is a positive integer, or sorry, in even and odd, sorry. So we have two conditions. Integer can be even or integer can be odd. So one condition is we will take that x is an even integer, and then we prove the statement that the answer is also is an odd integer. Then in the second part, we will take x is an odd integer, and we will put the values of x in the given function, and then we prove at the end that our answer is an odd integer. So in both cases, whether we have taken it an even integer or we are taking it as an odd integer, in both cases, if the answer is an odd integer, then this is the case, this is the way we have proof of a statement. So we will go around it. In the first condition, I will write if x is an even integer, when x is an even integer. So our function which is given to us is fx you can see x cubed plus x plus 1. So if I am saying that x is an even integer, you know about the definition of integer. If it is an positive, it's an even number, then it will be like this form, 2n, right? So wherever is x, we will put the value of x is equal to 2n. Why? Because this is the definition of even number, that it can be written as 2n, where n is an integer, positive or negative. So this is the statement. So I am using the statement of an even integer, and I take x is equal to 2n, and here I will write n, where n is positive or negative integer, and 2n will show that it is an even number. So f 2n, wherever is x, I am just replacing the value of n, x, like that. Then I am going to solve it, right? Just I am solving it. From these two, I can take 2 as common. Then I have left 4n cube plus n plus 1. Make 1 as a separate. Why I am taking it as separate, I will tell you at the end. You can easily understand why I am taking this one. Now, if n is an integer, then 4n cube plus n is also an integer. If n is integer, then automatically 4n cube plus n is also an integer, maybe positive or negative, whatever the case will be, right? So if this one is an integer, then according to statement you have to write each and everything, because if you want to get the marks you have to write each and everything, every statement according to statement of an odd number. No, the statement shows that odd number is 2n plus 1 form, this form, and my this answer is also of this form. You can see 2 something integer plus 1. So this shows definition of the statement of an odd number shows that equation 1 statement is an odd number. Why? You can check. 2 something multiply, which is an integer, plus 1. This is the definition of odd number. 2n plus 1 is an odd number. And my answer is something like that. 2 something integer plus 1. So this shows, and this statement of odd number shows that our this statement is an odd number. So is in this way I have proved it for the case when x is an even number. But in the second condition, if x is an odd number, then take x is an odd number, like I will take in the form 2m plus 1. This is the definition of odd number. The value of x is equal to 2m plus 1. I put this value of x is equal to 2m plus 1 in the given function, which is this function, which is fx is equal to x cubed plus x plus 1. Just I am going to replace the value of x which I have taken in case when it is an odd number. So our statement will become f. In place of x I am using this whole value of odd number. Whole cube, right, plus in place of x I am using only 2m plus 1, and the statement shows there is plus 1 also. So when I am going to simplify it, it will be like right. No, when we are taking, we have two terms like these terms, 2m plus 1 and 2m plus 1. What we will do, I'm taking from these two terms, taking 4m as common, then I have left here m plus 4m squared, sorry, and plus 1, and from here it is 8, sorry, 2 times 2 is, the 2 cube mean 2 times 2 is 4, 4 times 2 is 8, so it is 8 cube, and here we have left 2m, taking 1 as common from here, so I will write them in square brackets because they are separate from this statement. Okay, so in here 2m plus 1, 2m plus 1 is further common, take it as common, and you will left here 4m square plus 1 from this statement, and here we have already 2m plus 1 and plus 1 will remain as it is. Now from this term, whole term, and from this whole term, what I am going to do, I am taking 2m plus 1 as common, and I have left here 4m square plus 1 plus 1, right? So 2m plus 1, 4m square plus 2, right? further from this term I'm taking 2 as common. You can take 2 as common. 2m plus 1 will remain as it is, but from here I am taking 2 as common, then here it is left 2m square plus 1 and plus 1. No, you can easily check that this 2m plus, if m is an integer, then 2m plus 1 into 2m square plus 1 will also be an integer. And you can check it is taking some form. Some form mean if this is an integer, then 2 multiplied by integer plus 1, it will be an odd integer, right? So you can write, you can do the statement like that. If m is an integer, then 2m plus 1 multiplied by 2m square plus 1 is also an integer. So 2 multiplied by this integer and 2m square plus 1. So 2m form plus 1 is an odd integer. So in this way we have proved that if n is an odd integer, n is an odd integer, our answer is an odd integer, right? So this is the way we proved it. And you can check here, if you want to check here, if x is an even integer, then it can be written as for some integer substitute x equal to n into the function. We have done this and we have proved this like that. And if fx is odd when x is even, right? If x is, this statement is done when it is odd, x is even, fx is odd, we have proved it. And when x is an odd integer, then we have proved that fx is an odd integer. So in both cases, fx is odd when x is odd. So fx is odd when x is even and when x is odd. We have proved it. I have done the proof in front of you. I have taken x one time an even integer and x and one time as an odd integer, and then we at the end the answer we prove that this is an odd integer. So this is the case, and in this way we prove this statement that fx is odd when x is even and x is odd. As any integer x must be either odd or even, you have therefore shown that fx is odd for any integer, and this statement is true. In this way you will prove the statements. It's a little bit logic way, but if you understand the logic, then you can easily prove it in a way, in a logical way. It is very interesting. Hopefully you will get it. Just you have to keep in mind the statement of even number and the statement of odd number. Thank you.